So, friends, in the part 1 of the group 18 inert gases of the P block elements, we cleared or rather we covered the physical properties. Now we are moving up with the chemical properties. Generally, it is said that when you are discussing the inert gases and that too the chemical properties of inert gases, it is very clear that they have very less reactivity. They do not react very much. What is the reason behind them having less reactivity or least reactive? In the other words, you can say that they are having the property of inertness or being inert. The reason is they have completely filled shell. What do you mean by completely filled shell? Completely filled shell over here indicates that their octet is complete. They do not rather require electrons to gain or to lose. And you can see this when you compare helium alone, it is 1s2. But when you have neon, argon, krypton, xenon, radon, and even argonison, you have its general electronic formula as Ns2np6, and which indicates it to be highly inert, hence chemically inactive or rather less reactive. In the other words, if you see very clearly, the value of its ionization enthalpy is very much high and it has more positive electron gain enthalpy. Having high positive electron gain enthalpy and higher value of ionization enthalpy indicates it to be yet very clarified, having the property of being inert, and these are the reasons that noble gases do not react very quickly and tend to be inert. Now, although they are inert, there were few scientists in that era of 60-62 who were behind noble gases to find some of its reactivity. And Neil Bartlett in 62 or somewhat around that could identify a molecule that is O2 plus P2 PTF6 minus. The reason behind getting this molecule was least reactive platinum. Now he realized that the first ionization enthalpy of xenon and that of oxygen were very near to each other. And when the ionization enthalpies of xenon and oxygen were found to be near to each other, he thought of coming up with another molecule and he got a red colored compound which consisted of xenon and fluorine together in the form of XePtF6. This compound was obtained by a very simple reaction of platinum hexafluoride with xenon. This was the first ever molecule discovered by Neil Bartlett where xenon showed a property of getting combining with something else. After this discovery, a number of xenon compounds, mainly with most electronegative atom, either fluorine or oxygen, came into existence. Remember this statement very well. After this discovery of Xc plus PtF6 minus, a number of xenon compounds, mainly with most electronegative atom, that is oxygen and fluorine, came into existence. The compounds of krypton are very few, and the very popular compound of krypton is KrF2, which is popularly known as krypton difluoride. Compounds of radon have not been yet isolated. Only identified compound which is used in the radio tracer technique is radon difluoride, that is RnF2. So you are very well aware now that there are very less compounds available with radon, that is radon difluoride. You have krypton difluoride and very few compounds of xenon available with you. Although xenon after this had been found to prepare several compounds. We will divide it into three different ways, one of which is xenon fluorides, second one will be xenon oxides, and third one will be xenon plus oxygen plus fluoride. So initially three types of compounds came into existence. XeF2, the compound, or rather to say the molecule only made up of xenon and fluorine, XeF4 and XeF6. Later on, scientists came up with xenon trioxide, pardon me, and after that, xenon oxy tetrafluoride and XeO2F2. So, these are few of the compounds which can be obtained when you have a xenon reacting with highly electronegative element fluorine, or xenon reacting with highly electronegative element oxygen, or sometimes you get a combination of oxygen plus fluorine plus xenon. So now our first task is to learn the procedure, or rather to say the synthesis of getting XCF2, XCF4 and XCF6. Then afterwards, we will move with a very important concept, that is its structure on the basis of VSCPR with my own shortcut which I have learned looking to many videos and many references online. Coming to the first component of what we are learning, that is XeF2. XeF2 could be synthesized by a very general reaction where you have xenon in its gaseous state combining with difluorine in presence of 673 Kelvin temperature and 1 bar pressure. Over here, there is one important thing, that xenon must be used in excess amount because it is very less reactive, so it will be needed in more amount to undergo a reaction, and therefore it gets converted into XeF2. Similarly, when you have a xenon and you react with 2F2 at an elevated temperature of 873 Kelvin and 7 bar pressure, you end up with XeF4. Remember friends, Xe plus F2, excess of Xe at 673 Kelvin always gives you XeF2. Xe plus 2F2 at 873 Kelvin, 7 bar pressure always gives you XeF4, and Xe plus 3F2, that is the latest reaction where temperature is decreased to somewhat around 573 Kelvin. But as you decrease the temperature, you have to increase the pressure over here, and this results in the formation of XeF6. So consequently, you are done with xenon difluoride, xenon tetrafluoride, and xenon hexafluoride. So this is how xenon could react with electronegative atoms like fluorine and result into xenon difluoride, xenon tetrafluoride, and xenon hexafluoride. Moving in the similar fashion, you can also produce the same type of molecule, that is XeF6, by a little different reaction where you react xenon tetrafluoride with O2F2. It is a difluorine peroxide which reacts into XeF6 plus and O2 molecule. Over here, there is an interesting thing, and that interesting thing is the structure of fluorine difluorine dioxide, which is very much similar to that of hydrogen peroxide. We generally we coin it as open book structure. So over here, XeF4 when reacts with O2F2, it results in the formation of XeF6 and O2 is liberated. This is how you come to a conclusion where you have XeF2, XeF4 and XeF6, which are colorless crystalline solids and sublime readily at 298 Kelvin. They are powerful fluorinating agents. Now this is very important terminology. They are powerful fluorinating agents which very well indicate that they can be useful to add fluorine to some other reagents. If I have something like A and I react XeF2 with that A, then A will get combined with that F2 and Xe will come out. So this Xe was able to donate this F2A, and henceforth we could say that XeF2 or at a later stage XeF4 or XeF6 can very well act as powerful fluorinating agents. They are readily hydrolyzed even by traces of water. For example, when XeF2 is hydrolyzed to give Xe plus HF plus O2. This is a very popular reaction and I will try to explain it over here to you. You can look very well when you have xenon fluoride, ample of amount, reacts with 2H2O, that is proper quantity or the stoichiometric quantity of water. It results in the formation of xenon. Along with xenon, you get hydrofluoride. But important thing, apart from these 2 moles of xenon and 4 moles of hydrofluoric acid is dioxygen molecule. Now the question comes, why? Remember the definition of oxidation and reduction. If I say that hydrogen is added it's reduction. But if I say hydrogen is removed, very good, oxidation. Over here, you very well look onto the reaction. Here you have 2 moles of XeF2. It combines with 2 moles of H2O. See, H2O itself has hydrogen in it. But you see O2 coming out, it does not have any hydrogen. So the oxygen pairing with hydrogen in the molecule of water was able to remove that hydrogen. So if someone removes hydrogen from itself, it itself gets oxidized. So over here, we can say that XeF2 is hydrolyzed to give Xe plus HF plus O2. But in another sense, we can say that XeF2 can be used for oxidizing water to dioxygen. Is it true? For that, xenon should get reduced. And yes, xenon is getting reduced. On the left, you have XeF2 where Xe is plus 2. On the right, you only have an Xe which is 0. That is the oxidation states which we have been counting since redox. So friends, keep this thing very well in your mind. Now, keeping these three terminologies in mind, that is XeF2, XeF4 and XeF6, that is xenon difluoride, xenon tetrafluoride and xenon hexafluoride. Over here, there is a stanza where you can see that the structures of the three xenon fluorides can be deduced from VSEPR. They are shown in the figure. XeF2 and XeF4 have linear and square planar structures, where XeF6 has 7 electron pairs and would thus have a distorted octahedral structure. Over here, I would first of all like to draw your attention to three beautiful structures: a linear structure of XeF2, a square planar structure of XeF4, and a distorted octahedral of XeF6. As of now, there are three structures. It is easy to remember. You won't face any difficulty. Very well, all of us would be able to write that, sir, this is linear in shape, this is square planar in shape, and this is distorted octahedral in shape. But friends, what I mean to say over here is little different. If you have more than 30-40 structures, how would you remember each structure? There are few shortcuts for that. What I have been doing over here, I will be just making you learn two or three things over here. But for a longer journey, along with this video, I will link up another video where I am just going to show the tricks to find out what is hybridization, what is the number of bond pairs, what is the number of lone pairs, how can we determine a geometry, and how can we determine a shape. And I'll make you understand here by taking all these examples. Let us start with XeF2. Friends, remember very well, always while deducing out using a shortcut, hybridization, bond pair, lone pairs, structure, geometry or shape, you should first of all know the number of valence electron in each of the atoms. And over here, if I say xenon has 8 valence electron whereas the fluorine has 7, you have to sum up the number of valence electrons of each atom first of all. So over here xenon has 8, one fluorine has 7, you have two fluorines. So you would end up by writing 8, 7 twos are 14 and the total will be 22. If I am not mistaken, I can write the number of valence electron in XeF2 to be 22 if I consider 8 valence electron of xenon and 7 each for a fluorine in XeF2. Now remember, if you get this answer, that is the number of valence electron somewhere between 2 to 8, you divide that number by 2. But if you get that answer between 9 to 56, you divide it by 8. Friends, over here, I am getting that answer somewhere between 9 to 56. So, when my answer comes somewhat around 9 to 56, what am I supposed to do? See, I will take this number 22, I will divide it by 8 because it is in this range. So, I'll end up with 8 2 times 16. I am left with 6. Always remember, this division should get finished in 2 steps. Now it is 6, so it is in the first range between 2 to 8. So I'll divide it by 2. 2 3s are 6. If it does not end in 2, either you are making some mistake or our formula is not working. But most of the cases of what you are supposed to learn in this next coming academic year of 2020-21 and the coming academic years for the people who will look into the video at a later stage. This works in most of the cases for what purpose you are here to learn. So over here, I have the answer 2 and 3. So I will write 2 plus 3. I will make a total of 5. Remember, if my total is 2, it is sp hybridization. If my total is 3, it is sp2. If my total is 4, it is sp3. If my total is 5, it is sp3d. If my total is 6, it is sp3d2. And if my total is 7, it is sp3d3. Over here, the total is 5, and therefore my hybridization is sp3d hybridization. Generally, sp3d hybridization gives a trigonal bipyramidal structure geometry. But here we are talking of the shape. Now, the first number always is the bond pair. Second number always is the lone pair. So over here, friends, total bond might be 5. But of those, only two are bond pairs. So a xenon in between can form only two shared pair, and that is with the fluorine, where the rest of the three would be lone pairs. And we are not as of now interested in lone pair, we are only interested in bond pair. If we would have been interested in all, then definitely we would have come up with the structure which would have been trigonal bipyramidal. But as of now, we are not interested in this bipyramidal. We are only interested in one aspect, and that aspect is a linear shape of XZF2. So always try to look to the number of bond pairs and on that basis deduce a structure. It is over here XZF2. So this is a methodology, or rather to say a shortcut, to be remembered if you are aware of VSCPR rules. Coming to XZF4, now I will go little fast. Xenon is 8, 1 fluorine is 7, you have 4 fluorines, so it will become 28, so total of 36. When the total is 36, friends, it is in the range number 2, so divided by 8, 8 fours are 32, 4, the range number 1, so 2 twos are 4, it's a 0. So 4, 2. Total is 6. When the total is 2, SP. When the total is 3, SP2. When the total is 4, SP3. When the total is 5, SP3D. When the total is 6, SP3D2. And when the total is 7, SP3D3. Over here the total is 6. And so my hybridization will be SP3D2, where 4 are bond pair and 2 are lone pair. Generally SP3D determines octahedral. So over here xenon will show a structure of octahedral, but when you will come to the shape, only bond pairs are counted, lone pairs are not counted, so these two lone pairs will not be counted, and henceforth it will only end up with a square planar shape. So remember, it's a square planar shape when it comes to XEF4, and on the screen also you can see over here it's a square planar shape. So this is how, friends, we work when we are supposed to learn the chemical properties along with their structures, geometries and shape. So over here we are clear that XZF2 is linear and XZF4 is square planar. Similarly, you can try XZF6. You will get the answer of the total number of electrons over here to be 50, because one fluorine has 7. You have 6 fluorines, so 7 6 are 42, plus 8 of a xenon makes it 50. When you will try to divide it by 8, you will get 8 6 are 48. You will be left with 2, and 2 ones are 2. So it will be a 6 plus 1 concept, a total of 7. Will always determine sp3d3 hybridization. But as it is a 6 plus 1, we will always end with distorted octahedral. So it's a distorted octahedral coming up when you will try to learn. So this is how, friends, we have just seen three different structures on the basis of the molecules that we have come up with, that is XZF2, XZF4 and XZF6. Now moving in the same momentum, we will now be learning over here two basic reactions which are generally asked at competitive phases of the examinations. What are those? When I have a xenon difluoride and I react with PF6, rather to say sorry, PF5, it always gives me a combined product, that is XZF whole to the power plus and PF 6 whole to the power minus 1. So this is how xenon difluoride reacts with PF5. Over here we have xenon tetrafluoride reacting with antimony pentafluoride, and when this antimony pentafluoride reacts with xenon tetrafluoride, we always end up with XeF3 to the power plus and SbF6 to the power minus. My motive behind writing these reactions is, if you go back and see the paper that was earlier over here, we were generating, or rather we were preparing XeF2, XeF4 and XeF6, whereas over here we are converting something new from XeF2, XeF4 and XeF6. So we can write the first reactions to be preparations of xenon difluoride, tetrafluoride and hexafluoride, and over here you can mention chemical properties of xenon difluoride, hexafluoride and tetrafluoride. Now coming to XeF6, it combines with uh, MF, where M can be sodium, potassium, rubidium or cesium, that is group 1 elements. It always ends up with XeF7 to the power minus 1 and only M plus. So this is how it works. So these are the three basic reactions which are generally called the chemical properties of xenon fluoride compounds. Earlier what we have learned over here are the preparations of xenon fluoride compounds, and over here what we were just now seeing are the chemical properties according to me regarding the xenon fluoride compounds. Now we are coming to the xenon oxygen compounds. We have only one compound alone to be xenon oxygen in our syllabi, and that is XeO3, and there are two popular reactions for it. One of them is XeF6. When combines with three molecules of H2O, it reacts and forms 6HF plus XeO3. Remember this very well. When you have xenon hexafluoride undergoing hydrolysis with three molecules of water will always reshuffle out as 3 hydrogen and 3 by 2 oxygen. This 3 moles of hydrogen will combine with F6, and this jointly will result into 6HF, and on the other side 3 by 2 O2 combines with xenon and gives you XeO3. So this is how it works. Generally you have seen H2O breaking as H plus and OH minus, but over here you are seeing something that is different. So this is how you have a basic reaction going on. Coming more into detail, you have xenon tetrafluoride 6 moles and combines with 12 moles of water. Initially, you end up with 4 moles of xenon plus 2 moles of xenon trioxide plus 24 moles of HF plus 3 moles of O2. So this is how you end up writing xenon tetrafluoride combined with 12 moles of water, resulting into 4 moles of xenon plus 2 moles of xenon trioxide plus 24 moles of HF plus 3 moles of O2. So this is how you can conclude by saying that these are the two, that is xenon oxide molecules. So this is xenon trioxide. In the same journey of xenon trioxide, if you look into carefully, I am for a while skipping these two reactions and I am focusing on this structure along with the same, that is XeO3 structure. We can see on the board that when we write XeO3, it looks something like this. So looking at the geometry, it is tetrahedral. Looking at a shape where the lone pairs are not counted, only bone pairs are counted, it is pyramidal. I think it won't be visualized, but it is pyramidal. If I show you like this, it is pyramidal, it is tetrahedral. Whenever you are counting the geometry, you go with both bond pairs and lone pairs, so it is tetrahedral. Only with the shape, it is like this, and henceforth I will coin it as pyramidal. But if we go with our shortcut previously taught to you in the same video, will it work or not? Let us check. Xenon has 8 valence, 1 oxygen has 6, that is 2s2 2p4. We have 3 oxygen, so it is 18. So it is 18 plus 8, 26. Now let us cross check. 26, 8, 3s are 24. You are left with 2. 2 ones are 2 0. So it is a 3 plus 1 chemistry. Total is 4. When the total is 4, it is sp3, and when it is sp3, its geometry has to be tetrahedral. But you have to only count for the bond pairs while going for the shape, and therefore what we did was right, it is pyramidal. And always remember, this 3 denotes the sigma, sigma and sigma bond between Xe and O. Pi bond also is not available in our formula. So make it very clear that lone pair is the second value, bond pair is the first value, and over here bond pair will only denote the sigma bonds. It will not denote the pi bond for our formula. This is how we could conclude by saying that we have four syntheses: XCF2, XCF4, XCF6, and XCO3, along with four popular structures, that is a linear shape of XCF2, square planar for XCF4, a distorted octahedral for XCF6, and a pyramidal for XCO3. Now let us learn oxygen, fluorine, and xenon in combination, giving two different structures, XeO2F2 and XeOF4. While synthesizing XeOF4, there is a very normal reaction where xenon hexafluoride undergoes hydrolysis, where 2 moles of HF are removed, and we end up with XeOF4. This is how we prepare XeOF4. Now, the same XeF6 undergoes 2 moles of hydrolysis. You end up writing 4 moles of HF plus XeO2F2. So, over here it is xenon dioxide difluoride. So, xenon oxy difluoride. So, this is how we can prepare XeOF4 and XeO2F2. I am giving you a little task on your side. XeOF4 is already given over here in the form of square pyramidal. You can do it by the formula we have learned. What about XeO2F2? Try yourself. You will come to the answer when you have doubt. I just tell you it will look like this. For a better support of yours, and you will have one lone pair on the top. This is how it will look. Technically speaking, it's a trigonal bipyramidal geometry, a little distorted one, but people call it seesaw. So this is how it works. Whenever you will learn XeO2F2, you will come up with the shape, and that shape will be seesaw. I am not discussing it completely. There should be a little part to be done on your side. So this is how we have come, or we are on the verge of completing the chemical properties, where you can see the synthesis of XeF2, synthesis of XeF4, synthesis of XeF6, synthesis of XeO3, along with XeO2F2 and XeOF4, and we have also learned chemical properties for XeF2, XeF4, and XeF6. Along with that, five structures are on your reference. The sixth structure, which was missing on the reference or which is not given in your reference, that is XeO2F2, I have already populated over here, which can be later on copied because you are watching the video and it is available over there with a beautiful shape seesaw, and making it very clear it is also not seesaw, it is distorted seesaw. But let us keep seesaw according to a few references. Now these were the chemical properties. Over here, there is a little stanza given where XeO3 is colorless explosive solid and has a pyramidal molecular structure, and XeOF4 is a colorless volatile liquid and has a square pyramidal molecular structure. I have given you a job at your home of making yourself the structure of XeOF4 using my formula, where you can add up the valence electron, and if the total number comes between 2 to 8 divided by 2, and if it comes between 9 to 56 divided by 8. As of now, we don't want to go above 56, although it is possible. So this is how, friends, we have completed the chemical part or the chemical properties of the group 18 elements, which are either called noble gases or called inert elements. There is a paragraph over here which insist us on learning, or rather discussing, the uses of inert gases. I am leaving it to you so that you will learn it, you will go through it, you will try to find new words. There are few statements like nuclear reactors, cryogenic agents, MRI systems, NMR spectrometers. These are 4 to 5 new terms which I insist you to go on the web, search by yourself, and learn a little, which will be a two-way process even for me and even for you in this part of online learning. So, probably I have completed the group 18 in this part 1 and part 2, and I am sure that we are not left with group 1 or group 2. Sorry, group 18, that is part 1 and part 2 of the video. We have completed the physical properties, we have completed the chemical properties of the requirement for you in your examinations. So the next video would be P block elements, but rather than going into group 18 now, we would have been shifted in group 17, that is halogens. As of now, we have completed this group 18, and if you find any queries, you can contact me at any moment to learn anything related to group 18. Thank you.